Hey everyone, welcome back. Ready to dive into some seriously cool industrial tech.
Always up for that.
Today we're tackling steam. I've been looking over these materials about using it as a heat source in industries, and, well, let's just say it's way more interesting than I thought.
It's fascinating stuff, really.
What's got me hooked is this idea of steam being a, heating powerhouse for industrial processes. I mean, yeah, it's hot, obviously, but what makes it so special, so efficient compared to other heat sources?
It boils down to, the efficiency. Steam's got this incredible ability to hold and release huge amounts of heat energy, way more than you'd think.
Really?
Oh, yeah. Especially when it, changes between being water and steam. It's like, imagine a delivery truck, right? But instead of packages, it's carrying a massive payload of heat and can drop it off exactly where it's needed.
Okay, I'm officially intrigued. So it's not just about steam being hot, it's about that extra concentrated heat energy it can deliver.
You got it. And the key to all that energy is something called latent heat.
Latent heat, right. That rings a bell, but remind me.
Okay, so picture this. You're heating a pot of water on the stove. Yeah. It takes a certain amount of energy to get the water boiling.
Makes sense.
But here's the thing. Even when that water is bubbling like crazy, the temperature stays pretty much the same. Around 212 degrees Fahrenheit or...
100 degrees Celsius for those listening in metric.
Exactly. So the question is, where's all that extra heat energy going if the temperature isn't changing?
Right, it's like vanishing into thin air.
Not vanishing. It's going into transforming the water from liquid to gas into steam. And that, my friend, is the latent heat at work.
So it's storing the energy.
Exactly. It's like steam is holding on to this extra energy until boom, it's time to release it. And when that steam hits something cooler and condenses back into water, all that stored latent heat gets released.
So it's not just hot, it's got this reserve tank of heat energy ready to go.
Precisely. That's what makes steam such a powerful heating method. It can absorb tons of heat,
Yeah,
move it efficiently, and then release it with a
the targeted blast.
perfect way to put it. No wonder so many industries rely on it.
It definitely makes those caution hot contents warnings on coffee cups seem a bit more serious, doesn't it? If a little steam can do that.
Right. Imagine industrial scale.
Exactly. And speaking of scale, the material I read mentioned different types of steam. What's the deal with that? It's not all the same.
Oh, definitely not. Just like anything else, you can have variations. And that often comes down to the pressure of the steam.
Pressure. How so?
Think about it. The type of steam, how it behaves, really depends on its pressure, which changes the boiling point of the water. Higher pressure means a higher boiling point.
So you're saying you can make water boil at different temperatures?
Exactly. At normal pressure, we all know, 100 degrees Celsius, right? But crank up the pressure, and suddenly you can have water boiling at much higher temperatures.
Which creates these different types of steam.
You got it.
Okay, so pressure is key. And the document throws around some terms that, well, they sound pretty intense. We've got saturated steam, which is also called wet steam. Then there's unsaturated or dry steam. And to top it off, we have superheated steam. It's like a whole vocabulary lesson just for steam. Can you break these down? Like, what makes them different?
Absolutely. Let's start with saturated steam.
Yeah.
This is like the basic type, fresh off the boil, so to speak.
And the document wasn't very kind, giving it that other nickname.
Yeah, wet steam. And it lives up to its name.
How so?
Think back to that boiling pot of water.
Yeah.
Wet steam is full of these tiny water droplets that haven't quite finished transforming,
So it's like it's still got some of that water clinging to it.
Exactly. It's hot, for sure, but it's also humid and definitely on the wetter side. Like, remember those super humid summer days?
The ones that make you feel like you're swimming through the air.
Exactly. That's wet steam for you.
Okay, got it. But if I'm reading this right, wet steam isn't what you want for most industrial uses, is it?
Not really, no. It's got to do with those water droplets, see? They haven't released all their latent heat yet.
Ah, they're holding out on us.
In a way, yeah. Like little energy hoarders.
So it's not just about being wet, it's about the droplets holding back some of the heating power.
Exactly. And all that extra moisture, it's not doing any favors either.
Yeah.
Corrosion in pipes, less efficient heat transfer, can even mess with equipment. Not a recipe for efficiency.
Okay, I get it. Wet steam, not ideal. So what about the dry steam, the unsaturated one? Why is that the star of the show?
Unsaturated steam, that's the sweet spot. It's produced at a lower pressure, which means fewer of those pesky water droplets.
So less chance of those little energy thieves sneaking in.
Exactly. It's still got all that heat, ready to release its latent energy effectively, but without, the soggy baggage.
A much cleaner burn, so to speak.
Exactly.
So it's about finding that balance. Enough pressure for the good stuff, but not so much that you end up with a wet mess. Makes sense why it's the go-to for so many things. But what about this superheated steam? That sounds kind of intense, honestly.
It does, doesn't it? Imagine taking dry steam and just cranking up the heat even more.
Really push it to the limit.
To beyond the limit, actually. We're talking temperatures way above boiling. At that point, it's almost acting more like a gas than a vapor, which is where things get really interesting.
How so? I was reading that it's actually not as good for heat transfer, which seems weird. You'd think hotter would mean faster heating, right?
You'd think so, but it's a bit more nuanced than that. The thing is, how well heat transfers isn't just about temperature difference, but also the speed of that transfer.
Okay.
And superheated steam, because it's so hot and acting more like a gas, it doesn't transfer that heat as quickly as dry steam. Like, imagine trying to warm up a cold room with a hairdryer on the highest heat setting but very low airflow.
It would take forever.
Exactly. It's not just about the heat, it's about how efficiently it can be transferred.
So superheated steam has its uses, I'm sure, but it's not the everyday champion.
Right. You wouldn't use a blowtorch to heat your soup, right? Different tools for different jobs.
Makes sense. So we've got our steam varieties down. But going back to those water droplets in the wet steam for a sec. The document mentioned something called steam drying to get rid of them. It's like we're doing laundry with steam now. What's the deal with these dryers?
Good one. Remember talking about condensation on a bathroom mirror after a hot shower?
Sure. Classic example.
Well, it's like that, but on a massive scale in industrial settings. And instead of a mirror, it's the insides of pipes carrying the steam. Not good.
Yeah, you can imagine. Clogs things up, right?
Exactly. And that means wasted energy, worse heating, potential equipment issues. Not good at all.
So these dryers are like the cleanup crew.
Exactly. They're like giant dehumidifiers, getting those water droplets out of the steam before they cause any trouble.
Okay, important job. The document mentioned two main types, a simple one and then a screw type. That simple one seems, well, pretty simple, just an obstacle course for the steam.
Pretty much. Picture a big container with a baffle, kind of like a wall inside.
Okay.
Wet steam comes in, hits that baffle, and suddenly has to change direction.
I'm picturing a sudden turn.
Exactly. And those water droplets, they're a bit heavier, have more inertia, and they can't make that turn so easily. So they slam into the baffle, fall to the bottom, and get drained away.
So the baffle's like a strategically placed wall to knock those droplets out of commission.
Exactly.
Ingenious, really. What about this screw-type dryer, though? Sounds way more high-tech.
It is a bit fancier. Instead of a baffle, it uses something called a helical element, basically. A spiral, a screw shape inside a cylinder. The wet steam enters and has to travel along this spiral path.
Okay, now I'm picturing a high-speed, steam-powered roller coaster.
And as that steam is whipping around this spiral, something really neat happens. It creates centrifugal force.
The force that, like, pins you to the wall of those spinning carnival rides?
The one and only. Now, those water droplets, they're denser than the steam, right?
Right.
So they get flung outward toward the sides of the cylinder.
While the steam gets to keep on cruising.
Exactly. The drier steam naturally continues upward, and those separated water droplets are left behind, ready to be collected and shown the door.
It's like a very elegant sorting system for steam.
Exactly. Efficient and effective.
I'm telling you, this is way cooler than I thought. But now we've got this perfectly dry, efficient scheme all ready to work its magic. How do we make sure it actually releases all that heat in the right place at the right time? Like, how do we keep it from escaping before it's done its job?
You've hit on a crucial point. Wasting steam is wasting energy, and nobody wants that.
True enough.
That's where the unsung heroes of the steam system come in. Steam traps.
Steam traps. That sounds kind of ominous.
Maybe a little, but trust me, they're pretty clever. Essentially, they're like special one-way valves.
One-way valve.
Yep. They let steam into the heating system, but make sure it doesn't sneak back out before it's done its job.
Ah, so they're like the bouncers of the steam world.
I like that. But instead of checking IDs, they're all about knowing the difference between steam that's ready to work and steam that's, well, got retired.
So how do they do that? How do they tell the difference?
That's where the real ingenuity comes in.
Yeah.
There are actually a couple of main ways these steam traps operate, and they're fascinating. Some of them use the density difference between steam and condensate,
Condensate being the water that forms when the steam cools down.
Exactly. And then other traps use temperature differences to do their thing. But why don't we dive into the specifics of those after a quick break?
All right, so back to those steam traps. You were saying some use density, others use temperature.
You got it. So The density-based ones are often called mechanical traps. The simplest one to picture is the float trap. Imagine a little chamber with a floating ball inside.
Okay, I can see that. Simple enough, but how does it actually trap the steam?
Well, as that condensate flows into the trap, it lifts the float, right? Gets to a certain level and boom, the float pushes open a valve, letting the water drain out. But, and this is the key, the float's designed so that only the water can pass through, not the steam.
Ah, so it's like a gatekeeper, holds back the good stuff while letting the condensate escape. What about the bucket trap? Does that one actually have a tiny bucket in it?
No miniature buckets, but the idea is similar. Instead of a float, picture an upside-down bucket submerged in the condensate. Steam comes in, pushes the bucket down, which closes a valve. But as condensate fills up the space, the bucket loses its buoyancy, it floats up, and that opens the valve to release the condensate.
So both use buoyancy, just in different ways.
Okay.
Clever. But those are the density-based ones? You mentioned some traps use temperature, right? The thermostatic ones.
Exactly. Those are all about sensing temperature differences. Imagine a little capsule, right?
Mm.
It's got a special liquid inside that boils at a slightly lower temperature than water. So when it's surrounded by hot steam, the liquid boils, the capsule expands, and that closes a valve. But as condensate comes in and cools things down,
The liquid cools down too.
exactly, it stops boiling, the capsule shrinks back down, and that opens the valve to release the condensate.
It's like a tiny steam engine built into the trap itself. These are seriously ingenious little devices, but with so many options, how do they choose the right trap for the job?
It's a good question, and honestly, there's no one-size-fits-all answer. It depends on so many things: the steam pressure, the temperature they're working with, the specific application, even just the physical space they have to work with. Kind of like choosing the right tires for your car. You've got to think about the terrain, the weather, what you'll be using it for.
Makes sense. It's all about finding that perfect fit. But what if they get it wrong? What happens if you have a mismatched steam trap?
Oh, it can cause all sorts of problems. Wasted energy, for one, reduced heating efficiency, which no one wants, and in some cases, it can even damage the equipment itself.
So these little traps, they might be small, but they're kind of a big deal.
Absolutely crucial.
Wow, we've covered so much ground in this deep dive. The power of latent heat, the different types of steam, how they dry it, those amazing steam traps. I feel like I've gone through steam boot camp.
You've been a star pupil. And hey, next time you see steam in action, whether it's in a factory or just steaming up your veggies on your dinner plate, you'll know there's a whole lot more going on than meets the eye.
Absolutely. But here's something for everyone to ponder as we wrap things up. If steam is this powerful, efficient, relatively clean energy source, why aren't we using it more? What are the downsides, the challenges that might be holding it back? It's something to think about. And on that note, thanks for joining us for this deep dive into the fascinating world of steam. Until next time, stay curious.